Above us stretches an absence so familiar, we mistake it for permanence. A sky unbroken, a planet that seems finished, nothing circling but a single moon, and the distant lights of wandering worlds. It feels inevitable, as though Earth could never have looked any other way. Perhaps Earth once carried a ring. Earth looks complete today. Oceans are steady, continents settled. The sky is open and empty except for the moon and the wandering lights of planets. But planets do not begin to finish. Other worlds in our solar system still wear rings openly, Saturn most famously, but also Jupiter, Uranus, Neptune. Rings are not decorations. Scientists understand them as evidence of gravity pulling destruction into order. A ring is simply material trapped in orbit, dust, rock, ice, debris circling, bound by gravity. It does not need to shine. It does not need symmetry. If something breaks within a certain distance of a planet, tidal forces stretch it apart. Inside that invisible boundary, known as the Roche limit, material cannot gather into a moon. Instead, it spreads, forms bands, behaves like a ring. Earth formed in the same violent neighborhood as those ringed planets. Earth survived collisions powerful enough to melt its surface. Some impacts were immense enough to launch material upward with tremendous speed. Not all of that material would have escaped. Anything that fails to reach escape velocity must orbit, and orbiting material follows strict rules. If Earth ever held debris inside its Roche limit, gravity would not allow it to become a moon. It would thin, widen, and circle, and over time, gravity would also guarantee loss. Rings are often temporary. They form suddenly, they fade gradually, they leave little behind. But if rings are a natural outcome of planetary violence, why does Earth appear so bare? What happened to any orbiting debris born from Earth's earliest impacts? How long could such a structure have endured above a molten young world? And if Earth did lose a ring, what did that loss change in the sky above? Tonight, we trace the physics of destruction and consider whether our planet once looked fundamentally different from the one we know. But before we begin, if you enjoy these calm explorations like this one, I would appreciate it if you gave this video a like and perhaps tap subscribe. It helps other curious dreamers find their way to this peaceful little corner of the internet. And if you'd be so kind, let me know in the comments, where are you listening from tonight, and what time is it where you are? It's always a joy to see how far across the world this little sleepy corner of science travels. So now, take a slow, deep breath, let your shoulders soften, and together, let's step softly into the vanished halo that may have once circled our world. From far away, the word ring suggests something polished and luminous, a perfect circle drawn in light around a distant world. In laboratories and observatories, however, the meaning is quieter and less romantic. A ring is not defined by radiance or balance, nor by the dramatic sweep seen through a telescope. It is defined by motion and confinement. Material that circles a planet without escaping or settling, sustained by gravity and guided by orbital mechanics, is enough to earn the name. That material can be almost anything: fine dust drifting between collisions, shards of rock chipped from larger fragments, frozen particles of ice, irregular blocks of debris, all qualify. None of them need to form a smooth band. None of them need to reflect sunlight in a graceful arc. If countless pieces share a similar path around a planet and remain bound to it, they become a collective structure. Their shared orbit is the only requirement. Seen up close, a planetary ring would not resemble a solid hoop suspended in space. It would feel more like a swarm held in place by invisible rules. Each particle follows its own path, shaped by gravity, moving at its own speed according to its distance from the planet below. Those closer travel faster, those farther move more slowly. The result is not rigid harmony, but layered motion, a continuous rearrangement that still maintains an overall form. What looks like a single band from a distance is in truth a vast congregation of separate travelers. Symmetry is optional. Some rings are narrow and sharply bounded, others stretch thinly across enormous spans of space. Gaps can open where gravitational interactions clear certain regions, while neighboring lanes thicken where particles crowd together. A ring may be dense in one sector and sparse in another, clumped in places and diffuse in others. Its outline can shift over time as collisions redistribute material, grinding larger fragments into finer grains that spread more widely under the subtle pressure of light and gravity. Duration is equally flexible. A ring can endure for millions of years if replenished or stabilized, yet it can also fade on a shorter cosmic timescale. Collisions slowly reduce fragments to dust. Dust drifts inward or outward, depending on forces acting upon it. Gravitational interactions stir the structure, pulling some material down to the planet and nudging other portions away. The boundary between presence and absence is gradual rather than abrupt. A ring can thin to near invisibility long before it fully disappears. Because of this, beauty is incidental. A planet does not need brilliant arcs like those of Saturn to be considered ringed. Even a faint, uneven band of debris qualifies if it remains in orbit as a coherent structure. Earth would not have required a luminous halo to meet the scientific definition. A temporary disk of shattered rock, uneven and muted, circling above the surface would have been enough. In this way, the concept of a ring becomes less about spectacle and more about circumstance. It is a phase shaped by gravity, by collision, and by the delicate balance between escape and return. Whenever material is trapped in orbit and prevented from assembling into a single body, a ring exists, no matter how dim, how irregular, or how brief its presence may be. Gravity is patient. It does not need spectacle to shape a world. It works quietly, steadily, drawing mass toward mass, bending motion into curves that close upon themselves. In that constant pull lies both unity and fracture. The same force that gathers material into planets can also unmake what drifts too close. When an object approaches a massive body, gravity does not tug evenly. The side facing the planet feels a stronger pull than the far side, and the difference stretches the object along the line between them. This stretching, known as tidal force, is subtle at a distance, but it strengthens rapidly as space narrows. If the visitor is sturdy enough, its internal cohesion resists the strain. If it is fractured, loosely bound, or composed of rubble held together by weak gravity, the imbalance becomes decisive. The nearer side is drawn downward more fiercely than the far side can follow. Cracks open, pieces loosen. What was once a single body begins to fail along invisible fault lines. In extreme cases, the object does not merely split in two, it unravels into a stream of fragments, each inheriting its own path around the planet below. This process does not require drama. It unfolds as a quiet contest between internal strength and external pull. When the latter prevails, gravity transforms cohesion into dispersion. The fragments do not plunge immediately toward the surface. Their forward motion carries them sideways, even as the planet draws them inward. The result is orbit, a balance between falling and missing. Each piece becomes a traveler, circling rather than colliding, provided its speed and position fall within the narrow conditions that sustain this dance. Impacts offer another route to the same outcome. In a crowded planetary system, collisions are inevitable. When one body strikes another, the energy released can shatter rock, vaporize ice, and fling debris outward with tremendous velocity. Some fragments are accelerated beyond the threshold required to break free, escaping into wider space. Others, launched at slightly lower speeds or at different angles, remain gravitationally bound. They arc outward, slow under the planet's pull, and settle into elongated paths that gradually flatten into a shared plane through countless minor collisions. Within that plane, motion is organized by gravity's geometry. Faster fragments overtake slower ones, collisions grind larger chunks into smaller grains, energy is redistributed with each encounter. Over time, the swarm spreads laterally, thinning as it extends around the planet's equator, where angular momentum guides it most efficiently. What began as a violent dispersal became a structured band. The ring is not assembled in a single moment. It is refined through repetition, shaped by the steady logic of orbital mechanics. Such structures are often born from loss rather than growth. A moon that wandered too near, a passing body torn apart, an impact that scattered materials skyward. Each event replaces unity with multiplicity. Creation here is secondary. The ring is the residue of something undone, the after image of a body that could not remain whole under gravitational stress. Yet destruction in this context is not chaos without pattern. Gravity imposes order, even upon fragments, arranging them into trajectories that collectively trace a luminous or muted circle around the world they orbit. In this way, rings emerge naturally from the same laws that build planets. The boundary between assembly and disassembly is thin, governed by distance, speed, and strength. When those variables align unfavorably for a solid body, fragmentation becomes inevitable. When fragmentation occurs within the reach of gravity's embrace, the pieces are not scattered randomly into darkness. They are gathered into motion, compelled into orbit, and held there long enough to form a structure, born from breakage, yet sustained by the very force that caused it. Space around a planet is not uniform. Though it appears empty and continuous, it is structured by gradients of force that change with distance. Close to a massive world, gravity does more than pull. It differentiates. The side of an orbiting body nearest the planet feels a stronger attraction than the side turned away. Over small separations, the difference is negligible, but as distance decreases, the imbalance sharpens. At a certain threshold, the variation becomes decisive. This threshold is known as the Roche limit, a boundary not drawn in light, yet precise in consequence. Within this region, cohesion struggles to compete. A moon forming from loose material depends on its own gravity to gather fragments into a single sphere. That self-attraction must overcome disruptive forces attempting to stretch and separate it. Inside the Roche limit, tidal stress exceeds the internal gravity of a fragile body. Particles that drift together are teased apart before they can settle. What begins to assemble is gently undone, again and again, until accumulation gives way to dispersion. The result is not chaos, but redistribution. Material that might have merged into a companion world is instead sheared into streams. These streams flatten into the planet's equatorial plane, guided by angular momentum and repeated collisions. Clumping is suppressed, spreading is encouraged. The environment selects for extension over consolidation. Fragments align along shared paths, circling without merging, sustained in a pattern defined by constraint. The precise distance of the Roche limit depends on densities and composition. A rigid object held together by strong internal bonds can endure slightly deeper within the gravitational well than a loose aggregate of rubble. Icy material responds differently than dense rock, yet for any given planet and any given type of satellite, the boundary can be calculated. It is an expression of mass, radius, and structural strength, a mathematical line that separates formation from fragmentation. Earth possesses such a boundary as surely as any gas giant or ice world. Though less visually celebrated, its gravitational field establishes a similar region of instability for orbiting bodies. Any substantial fragment wandering inward past this limit would encounter increasing tidal strain. Cracks would widen, structural integrity would erode. Even a partially consolidated object could find itself disassembled into components following slightly divergent paths. In this zone, survival as a single body becomes unlikely. When material is produced within that radius, whether through collision, capture, or internal disruption, the outcome is guided almost automatically. Without the option to aggregate into a coherent moon, the fragments remain separate. Their orbital speeds differ subtly with distance, preventing long-term congregation. Collisions grind edges down, converting blocks into shards and shards into grains. A disk emerges, not by deliberate construction but by exclusion. The rules of the region do not permit anything else. This invisible boundary therefore acts as a sculptor. It does not create matter, nor does it inject energy into the system. It sets conditions under which certain structures cannot endure. Beyond it, satellites may grow. Within it, persistence requires dispersion. A ring becomes the natural architecture of material confined to this inner realm, an arrangement that reflects constraint rather than abundance. In this way, the Roche limit transforms proximity into outcome. It marks a transition from potential unity to enforced multiplicity. Around Earth, as around other planets, that boundary waits silently, shaping the fate of whatever drifts too near, guiding fragments into orbiting bands when consolidation is no longer possible. Before continents held their positions and oceans found their basins, Earth existed in a state that would be almost unrecognizable today. It was not yet the blue world of stable horizons and repeating seasons, but a sphere still assembling itself from the lingering debris of formation. Matter continued to fall inward, drawn from a crowded inner solar system where countless fragments crossed one another's paths. Growth was not gentle. It arrived through accumulation and collision, through the steady addition of mass delivered at immense speeds. The young planet carried heat from multiple sources. Gravitational compression raised internal temperatures as layers thickened. Radioactive elements, more abundant in those early days, released energy as they decayed. Most of all, impacts convert motion into heat on a global scale. Each collision transferred kinetic energy directly into the crust and mantle, melting rock and unsettling whatever temporary solidity had begun to emerge. The surface could not remain still for long. It softened, fractured, and reformed beneath continuous bombardment. This era, often referred to by geologists as the Hadean, was defined by instability. Large bodies, some tens or hundreds of kilometers across, struck with enough force to excavate vast regions of crust. Smaller debris arrived more frequently, peppering the planet in a relentless pattern. The atmosphere, thin and evolving, offered little protection against incoming material. With no oceans yet settled into permanence and no rigid lithosphere spanning the globe, Earth absorbed each event directly. Rock vaporized under intense heat, only to condense again as molten droplets that fell back through thickened air. Certain collisions were not merely surface events. They penetrated deeply, disturbing the planet's internal structure. Energy released by especially massive impacts may have melted large portions of the mantle, creating transient magma oceans that extended across vast regions. In such a state, differentiation continued, heavy elements sinking toward the core, while lighter materials floated upward. The planet refined itself even as it endured disruption. Formation and trauma unfolded simultaneously. Amid this turbulence, boundaries were provisional. Crust that began to solidify could be shattered by the next large strike. Basins that briefly collected condensed water might be vaporized again under intense heating. Earth's rotation, already significant, could be altered subtly by angled impacts that transferred angular momentum. The shape of the planet, the tilt of its axis, even the distribution of internal layers were subject to modification. Stability was not assumed. It was earned over time through the gradual decline of incoming threats. These processes did not occur in isolation. Nearby planets and smaller bodies experienced similar histories. The inner solar system was a dynamic network of interactions, with gravitational encounters nudging objects onto crossing trajectories. Earth's survival was not a matter of avoiding collision, but of enduring it. Each impact left traces in composition and structure, even if the visible scars were later erased by tectonics and erosion. Over millions of years, the frequency of large collisions declined as the available debris was either incorporated into planets or cleared from the region. The crust thickened. Surface temperatures began to moderate as radiative balance slowly asserted itself. Oceans condensed more persistently, buffering heat and moderating extremes. Yet the memory of those early traumas remains encoded in mineral grains and isotopic ratios, silent witnesses to a period when Earth was shaped less by calm evolution and more by repeated planet-scale upheaval. There was a moment in Earth's early history when the trajectory of another world intersected its own. The object was not a wandering stone or a modest asteroid, but a planetary body in the final stages of formation, often called Theia in modern models. Roughly the size of Mars, it traveled along an orbit that gradually converged with Earth's path, drawn into a closing spiral by gravitational interactions within the young solar system. When the two worlds finally met, the encounter reshaped them both. The collision was neither a direct head-on strike nor a gentle brushing contact. Simulations suggest an oblique impact, a glancing blow delivered at extraordinary velocity. The energy released in that single event exceeded anything Earth would experience again for billions of years. Rock did not merely fracture, it flowed like liquid under the intense heat generated in seconds. Vast portions of both bodies were vaporized, rising as incandescent plumes above the surface. The crust and upper mantle of the proto-Earth were partially melted, merging with material from the impactor in a turbulent exchange of mass and momentum. In the wake of the collision, Earth was transformed, its rotation accelerated, its internal layers stirred and partially homogenized. The shock wave traveled through the mantle, redistributing heat and altering density patterns deep within. Above the surface, however, the most dramatic change unfolded. Ejected material, composed primarily of silicate rock from both bodies, was launched outward at speeds that approached but did not consistently exceed escape velocity. Some fraction of this debris left the system entirely, flung into independent solar orbits, yet a substantial portion remained gravitationally bound. That bound material did not fall back immediately. Carried outward by momentum and then slowed by Earth's pull, it settled into elongated paths that gradually intersected and flattened into a common plane. Collisions among fragments were frequent in those early hours and days, grinding larger masses into smaller pieces and dissipating excess energy. What had once been solid crust became a swirling disk of molten droplets, vapor condensate, and fractured rock, circling Earth in a luminous haze. For a time, the planet was encircled by its own remnants, The disk extended outward from near the planetary surface to distances measured in tens of thousands of kilometers. Within it, temperature gradients and radiative cooling began to sort material by size and density. Heavier fragments traced slightly different trajectories than lighter vapor particles. The system was dynamic and evolving, governed by gravity, angular momentum, and thermodynamics working in concert. Nothing within that disk immediately resembled the moon familiar today. Consolidation required time. Repeated collisions allowed certain regions beyond the critical boundary where tidal forces were less destructive to accumulate mass more effectively. Clumps formed, merged, and grew, while material closer to Earth remained inhibited from coalescing. The entire structure behaved as orbiting matter first, a temporary ring born directly from catastrophic release of energy. Isotopic evidence preserved in lunar rocks supports this scenario. The chemical similarity between Earth's mantle and the Moon suggests a shared origin, consistent with mixing during that immense impact. Subtle differences in volatile content hint at high-temperature processes in which lighter elements were preferentially lost to space. Together, these signatures point back to a single transformative event. Before the Moon rose as a coherent sphere, there was this intermediate state, a circumterrestrial disk forged from collision. It was not yet a satellite, but it was already a structure in orbit, the raw architecture from which a new companion would gradually emerge. In the immediate aftermath of that planetary scale impact, the space surrounding Earth was not defined by a single companion, but by motion. Countless fragments traced elongated paths that intersected and diverged, bound by gravity yet still adjusting to the shock that had set them free. Nothing within that expanding cloud possessed the coherence required to become a moon at once. Consolidation demands patience, and patience in orbit is governed by collision and time. As debris completed its first revolutions, differences in velocity became apparent. Material traveling closer to Earth moved more swiftly, while fragments farther out lagged slightly behind. These variations caused paths to cross, leading to impacts that were frequent and energetic. Larger chunks shattered into smaller ones. Molten droplets merged briefly before being separated again. With each encounter, kinetic energy was redistributed and random inclinations were dampened. The chaotic swarm began to flatten, guided by the conservation of angular momentum toward a common equatorial plane. This gradual compression transformed an initially three-dimensional cloud into a disk. The thickness of the structure narrowed as vertical motion was exchanged for lateral spread. Collisions acted as a quiet sculptor, reducing height and encouraging breadth. Fine particles accumulated in extended bands, while heavier fragments carved more defined lanes through the mixture. Turbulence persisted, yet an emerging order became visible in the shared direction of travel. Within this disk, proximity to Earth mattered profoundly. Regions closer to the planet experienced stronger tidal forces, inhibiting stable accumulation. Farther out, where those stresses weakened, matter could begin to gather into denser clumps. The disk, therefore, contained contrasting zones, one where aggregation was possible and another where dispersion remained dominant. It did not present as a uniform ring, but as a layered system, transitional and evolving. Thermal conditions added further complexity. Much of the material had been heated to extreme temperatures during ejection. Vapor condensed into droplets. Droplets solidified into fragments. Some fragments collided and reheated upon impact. Radiative cooling gradually reduced overall temperatures, but gradients remained across the disk. These differences influenced viscosity and stickiness, affecting how easily particles merged when they met. In cooler outer regions, cohesion strengthened, while inner zones remained more fluid and fragment prone. Throughout this period, Earth itself rotated beneath the disk, its day shortened by the momentum imparted during collision. The interplay between planetary rotation and orbital motion shaped the disk's structure, reinforcing its alignment with the equator. Gravitational resonances began to subtly reorganize material into preferred distances, even before any substantial satellite had formed. The system behaved neither as a finished ring nor as a completed moon, but as an intermediate architecture shaped by competing tendencies. For a time measured perhaps in years to centuries, Earth was encircled by this evolving band of remnants. To an observer positioned at a safe distance, the planet would have appeared girdled by a broad, uneven halo of rock and vapor, its brightness fluctuating as fragments collided and dispersed. It was a ring in behavior, if not yet in permanence, governed by orbital mechanics and tidal constraints. Eventually, beyond the more restrictive inner region, concentrations of matter grew large enough to resist fragmentation. Those concentrations would continue their slow assembly into a single dominant body. Yet before that consolidation reached completion, the debris disk itself defined the sky, a transient ring born from collision, sustained by motion, and poised between dispersal and creation. Light would not have traced a perfect arc across the sky. The structure encircling early Earth would have been subdued, its presence defined less by brilliance than by persistence. Composed largely of silicate rock and cooling droplets rather than reflective ice, it would have absorbed much of the sunlight that reached it. Its color may have leaned toward muted grays and faint rust tones, shaped by mineral composition and the lingering glow of recently heated fragments. At certain angles, it might have appeared as a pale band, at others almost invisible against the brightness of the young sun. The ring would not have formed a single continuous ribbon. Density variations inherited from the chaotic debris disk would have persisted, creating regions where material clustered more heavily and others where it thinned into faint streams. From the surface below, it might have presented as layered streaks stretching from horizon to horizon, thicker near the equatorial regions and tapering as one moved toward higher latitudes. Its apparent width would have depended on viewing position, broad and imposing at some angles, narrow and diffuse at others. Because the particles followed slightly different orbital speeds, the structure would have been in constant rearrangement. Brighter patches could drift slowly relative to dimmer gaps, not because the entire ring rotated as a solid body, but because each fragment pursued its own path, governed by distance and gravity. Collisions would have generated fine dust that briefly brightened sections before spreading outward or settling inward. Over days and months, subtle changes in texture would have been noticeable to any observer patient enough to trace its evolution across the sky. Its edges would not have been sharply defined. Instead of a crisp boundary, the outer limits would have faded gradually into surrounding space, where scattered particles traced elongated paths before either joining denser lanes or descending toward Earth. The inner margin, closer to the planet, might have appeared more active, marked by a faint haze where tidal stresses and repeated impacts kept fragments in motion. At twilight, when sunlight struck the ring at a low angle, its silhouette could have sharpened, casting elongated shadows across the upper atmosphere. Shadows themselves would have shifted with latitude and season. Near the equator, the ring might have formed a persistent band overhead, filtering light during certain portions of the day. At higher latitudes, its presence would have varied more dramatically, rising and setting with orbital geometry. The sky beneath it would have carried a subtle alteration, a reminder that space above was not empty but structured. The texture of the ring would have resembled a weathered formation rather than a polished ornament. Larger fragments, perhaps tens of meters across, would have been embedded within a matrix of gravel and dust. Microscopic grains, produced through repeated collisions, would have scattered light unevenly. Occasional sparks from energetic impacts could have momentarily intensified local brightness before fading back into the overall dimness. In this way, the ring would have carried the visual character of aftermath rather than adornment. It would not have suggested symmetry crafted for display, but matter suspended in transition. Uneven, shifting, thicker in certain arcs and thinner in others, it would have stretched around the planet like a geological record written in orbit, less a jewel encircling a world than a transient scar, gradually softening as gravity and time continued their quiet work. Sunlight has always been Earth's primary sculptor, arriving in steady streams that warm the surface, drive atmospheric motion, and stir the oceans into circulation. When uninterrupted, it falls according to geometry, strongest at the equator, gentler toward the poles, rising and setting in predictable arcs. Yet a broad band of orbiting debris would have altered that familiar geometry, filtering and redistributing light before it ever touched the ground. A ring aligned near the equatorial plane would have cast a shifting veil across certain regions. At low latitudes, portions of the day might have unfolded beneath a faint, elongated shadow, a subtle dimming rather than a sudden eclipse. The effect would not have plunged the world into darkness. Instead, it would have softened direct illumination, reducing intensity during specific angles of the sun's path. The length and position of that shadow would change with Earth's rotation, sliding across the landscape in a daily rhythm governed by orbital mechanics rather than weather. Seasonal tilt would complicate the pattern further. As the planet leaned toward or away from the sun, the ring's apparent position in the sky would shift. At certain times of year, regions just north or south of the equator might find the ring intercepting more sunlight during daylight hours. At other times, the effect would lessen, allowing nearly unfiltered light to return. Higher latitudes might glimpse the ring lower on the horizon, its shadow stretched thin and diluted, barely perceptible, yet still measurable in accumulated energy balance. Light filtered through particulate matter carries a distinct character. Fine dust can scatter shorter wavelengths, subtly altering the color of the sky. A persistent ring could have introduced faint bands of altered hue during sunrise and sunset when sunlight grazed the disk at shallow angles. The atmosphere below would respond not to spectacle but to averages. Even a small reduction in incoming solar radiation, sustained over long intervals, has the capacity to shift temperature gradients between equator and pole. Climate operates on integration. The circulation of air depends on contrasts in heating. Oceans transport warmth through currents that respond to persistent differences in density and temperature. If equatorial regions received slightly less energy during portions of each day, the gradient driving large-scale convection might adjust. Trade winds could shift marginally in strength or latitude. Rainfall belts tied to thermal boundaries might drift over centuries, redistributing moisture across emerging land masses and early oceans. Such changes would likely be gradual rather than abrupt. A ring does not flicker on and off like a storm cloud. Its geometry evolves slowly as particles redistribute and density fluctuates. The surface below would experience a steady modulation of light, a quiet recalibration rather than a dramatic interruption. Ice formation at higher elevations or latitudes might advance marginally if reduced insulation persisted. Conversely, areas outside the principal shadow could receive slightly increased reflected light as sunlight scattering off the ring found new pathways to the surface. The interaction between ring shadow and atmospheric dynamics would introduce complexity without chaos. Regions accustomed to strong, direct sunlight might experience intervals of softened brightness, altering evaporation rates and surface temperatures by fractions that accumulate over years. Early oceans, still stabilizing after immense upheavals, would respond sensitively to such adjustments, as water's high heat capacity integrates subtle shifts over extended timescales. In this way, the presence of a ring would not merely decorate the sky, it would become part of the planetary energy budget, modifying how sunlight was distributed across latitudes and seasons. The changes need not have been dramatic to be influential. In climate systems, persistence is often more powerful than intensity, and a steady band of orbiting material could have shaped Earth's early environment through the quiet arithmetic of light and shadow. Nothing in orbit is truly permanent. Even when a ring appears broad and continuous, its existence depends on a balance that is constantly being eroded. The fragments that compose it travel at tremendous speeds, each tracing a path determined by distance from the planet and the subtle tug of neighboring particles. That motion gives a ring its structure, yet it also seeds its decline. Within the disk, collisions are inevitable. Particles do not move in perfect formation. Their orbits intersect slightly. Their velocities differ by small margins. When they meet, energy is exchanged. Some encounters are gentle, redirecting trajectories by degrees. Others are more forceful, grinding surfaces and breaking larger fragments into smaller ones. Each impact converts a portion of orbital energy into heat and internal fracture. Over time, the collective result is a gradual reduction in average speed. A decrease in speed alters altitude. In orbit, velocity and distance are intertwined. When a particle slows, even slightly, it can no longer maintain its previous height above the planet. Its path shifts inward, along a new, lower orbit. This descent may be measured in meters or kilometers over extended periods, but it is steady. The planet's gravity does not relent, it draws in what has lost momentum. As fragments spiral inward, they may encounter denser regions of the ring, triggering further collisions that accelerate the process. Fine dust produced through repeated grinding is particularly susceptible to additional forces. Radiation from the sun exerts a faint pressure, altering trajectories in minute increments. Interactions with the planet's magnetic field can influence charged particles, introducing subtle drifts. These effects are gentle compared to gravity, yet given enough time, they reshape the distribution of matter. Material is not lost only inward. Gravitational interactions among particles can also scatter some fragments outward. In multi-body systems, even minor perturbations redistribute angular momentum. A small portion of material may gain speed at the expense of neighboring fragments, moving to higher orbits where it becomes more tenuous and eventually escapes or disperses. The ring thus thins at both edges, shedding mass in opposite directions through different mechanisms. What makes rings inherently unstable is not vulnerability to sudden catastrophe, but exposure to continuous microscopic change. There is no need for an external disturbance to initiate decay. The internal dynamics of the system ensure gradual transformation. Collisions reduce size. Reduced size increases susceptibility to additional forces. Altered velocities lead to migration. The process resembles erosion, though it unfolds in vacuum rather than in water or wind. Timescales vary according to composition and environment. A dense ring, supplied by ongoing fragmentation, can persist longer than a sparse one with no replenishment. Rings composed of icy particles behave differently from those formed primarily of silicate rock, as reflectivity and cohesion influence temperature and collision outcomes. Yet across scenarios, one principle remains consistent. Without continual renewal, a ring trends toward dissolution. Eventually, enough material drifts inward to rejoin the planet or outward to dissipate into surrounding space. Density decreases, collisions become less frequent. The once prominent band fades into a thin scattering of isolated fragments. From a distance, the change is gradual, almost imperceptible in any single moment. Only across long stretches of time does the loss become evident. In this manner, a ring carries within itself the seeds of disappearance. It is a structure sustained by motion, yet diminished by the same motion. Even in calm orbital space, decay proceeds quietly, guided by gravity and cumulative collision, ensuring that no ring, however expansive at its birth, remains unchanged forever. Mass defines authority in space. The greater a planet's mass, the deeper the well it carves into the fabric of motion around it. Earth, though modest compared with gas giants, holds sufficient mass to exert a disciplined control over its surroundings. Its gravitational field extends far beyond the visible atmosphere, shaping trajectories and imposing structure upon anything that drifts within reach. Nothing near it moves independently for long. Objects that pass close are either captured temporarily or redirected with precision. Small bodies may find themselves tugged into elongated orbits, their paths bent sharply as they encounter the curvature of spacetime defined by Earth's mass. Some continue onward, altered but unbound. Others remain trapped, circling in arcs that reflect a balance between forward motion and inward pull. Yet even when captured, permanence is not assured. The region near Earth is dynamic. The planet rotates, its equatorial bulge influencing the gravitational field subtly but persistently. The moon traces its own path, adding rhythmic perturbations to anything in orbit. Solar gravity contributes additional gradients, stretching and compressing the system gently over time. Within this layered field, debris experiences constant adjustment. Slight irregularities in orbit amplify through repeated interactions, preventing static equilibrium from enduring. Low-altitude material faces atmospheric drag. Even a tenuous upper atmosphere can impart friction to fine particles and smaller fragments, especially during periods of heightened solar activity when atmospheric density expands. That friction extracts energy. As orbital speed diminishes, altitude declines. The process unfolds gradually, but its direction is fixed. Fragments descend along tightening spirals until they re-enter denser layers and burn or impact. Higher altitude debris avoids direct drag yet remains subject to gravitational complexity. Resonances with the moon can redistribute angular momentum, nudging fragments into new orbital configurations. Some gain slight increases in eccentricity, bringing them closer to Earth at one end of their path. Others are lifted outward, where perturbations from solar tides may eventually release them. In either case, the system evolves. Debris is sorted, reclassified, and rarely left untouched. Earth's gravity also contributes to aggregation under certain circumstances. Beyond restrictive inner zones, fragments can merge into more coherent bodies, reducing the number of independent pieces in circulation. As clumps grow, they interact differently with the gravitational field, altering the architecture of surrounding material. What remains as loose debris is gradually diminished through incorporation or elimination. Efficiency arises from persistence rather than forceful intervention. Earth does not actively sweep space like a broom. It establishes conditions under which unstable orbits decay and marginally bound objects are eventually removed. Over extended timescales, this cumulative effect clears the near environment. The chaotic aftermath of formation gives way to a cleaner system, not through a single dramatic event, but through continuous gravitational governance. In such a regime, orbiting debris cannot remain indefinitely in its initial configuration. Energy shifts, trajectories evolve, and losses accumulate. Some material falls inward, some escapes outward, some consolidates into larger forms. The overall mass, in loosely organized bands, decreases as time advances. Gravity ensures that what is unstable cannot endure without renewal. The present clarity of Earth's immediate surroundings reflects this quiet authority. The planet's gravitational reach, interacting with rotational and lunar influences, reduces excess matter over epochs. Even if a ring once encircled Earth in its youth, the same force that once gathered debris into orbit would have guided its gradual disappearance. Within Earth's domain, persistence without adjustment is rare, and eventual loss is woven into the fabric of motion itself. Long before it became the steady companion we know today, the Moon emerged from a field of orbiting remnants, gradually consolidating into a single dominant body. Once formed, it did not simply accompany Earth in silent symmetry. Its mass, though far smaller than Earth's, introduced a secondary center of gravitational influence within the system. From that moment onward, space around Earth was shaped not by one pull but by two, interacting in subtle and persistent ways. The Moon's most visible contribution is stability. Its gravitational torque moderates variations in Earth's axial tilt, reducing extreme shifts that could otherwise alter climate over long periods. By anchoring the orientation of Earth's spin, the Moon smooths out potential instabilities that might arise from solar perturbations or interactions with other planets. This steadying effect, measured over millions of years, has helped maintain relatively moderate seasonal cycles. Yet the same gravitational partnership that stabilizes the planet's orientation complicates the environment of any loose material in orbit. Debris does not experience Earth's pull alone. The Moon traces its path at a considerable distance, but its gravitational reach extends well beyond its visible disk. As it moves, it creates time-varying forces on particles that circle closer to Earth. These forces alter orbital elements gradually, shifting eccentricity, inclination, and alignment in ways that accumulate. A fragment traveling within a ring would feel periodic tugs as the Moon passed through specific configurations. When the relative geometry aligned, the fragment's orbit might elongate slightly, bringing it closer to Earth at one point and farther away at another. Increased eccentricity heightens the chance of interaction with denser regions of material, leading to collisions that reduce energy and hasten inward migration. Other fragments could be nudged outward, where perturbations from the Sun grow comparatively stronger. Resonances play a quiet but significant role. When the orbital period of debris relates to the Moon's period in simple ratios, gravitational interactions reinforce each other. These resonant zones can either clear material by destabilizing orbits or concentrate it temporarily before further disruption redistributes it. Over extended timescales, such pattern disturbances prevent the persistence of uniform, stable bands. The moon also influences the location of critical boundaries within Earth's gravitational domain. As tidal forces operate between Earth and moon, angular momentum is exchanged. The moon gradually recedes outward, a process measured today at a few centimeters per year. In earlier epochs, when it was closer, its tidal influence was stronger, intensifying perturbations on nearby debris. A nascent ring system existing during that era would have evolved under a more dynamic gravitational interplay than the comparatively settled configuration of today. Through these mechanisms, the moon acts as both guardian and agitator. It protects Earth's axial stability while subtly undermining the long-term coherence of orbiting debris. Material that might otherwise linger in orderly lanes finds its path gradually altered, collisions encouraged, decay accelerated. The process unfolds without spectacle. No single moment marks the transition from structure to dispersion. Instead, the cumulative effect of lunar perturbation ensures that marginally stable orbits become temporary. In this shared gravitational field, endurance requires isolation from disturbance, a condition difficult to achieve in the presence of a substantial satellite. Over centuries and millennia, the moon's influence compounds Earth's own clearing tendencies. Debris loses regularity, drifts from equilibrium, and ultimately descends or disperses. The quiet companion that steadies the planet's spin simultaneously hastens the fading of any fragile ring that once traced the sky. Beyond Earth and its moon lies a wider field of influence that never rests. The Sun, holding more than 99% of the solar system's mass, governs the motion of every planet and fragment within its reach. Earth travels around this central force in a path maintained by velocity and gravity in careful balance. Yet that balance is not confined neatly to the planet alone. It extends outward into surrounding space, shaping the environment in which any orbiting material must exist. The sun's gravity does not pull on Earth and its debris equally at every point. Just as tidal forces arise from differences in attraction across a body, solar tides emerge from gradients across the Earth-Moon system and the region nearby. The side of Earth facing the Sun feels a slightly stronger pull than the far side. The difference is small compared with Earth's own gravity, yet it is persistent and directional. Space around the planet is therefore subtly stretched along the line that connects it to the Sun. Within this stretched domain, orbits are gently distorted. A fragment circling Earth does not move in a perfect vacuum, defined solely by planetary mass. Its path is superimposed upon Earth's motion around the Sun. The result is a layered dance of gravitational influences. Solar tides introduce periodic variations in orbital elements, altering eccentricity and inclination by minute amounts that compound over time. Even without collisions or lunar perturbations, this steady external pull reshapes trajectories. For a ring composed of countless small particles, the effect is diffuse yet consequential. Each fragment experiences the sun's influence slightly differently depending on position and phase of orbit. The cumulative impact is a slow modulation of the ring's structure. Regions aligned more directly along the Earth-Sun axis may experience enhanced stretching, encouraging dispersion. Sections oriented perpendicular may feel comparatively compressed. These variations do not tear the ring apart abruptly. They function more like a continual flexing, a quiet oscillation imposed from afar. Over many revolutions, such oscillations redistribute angular momentum within the ring. Some particles gain slight increases in orbital energy when tidal geometry aligns favorably. Others lose energy during opposing phases. These imbalances propagate through collisions, amplifying the tendency toward migration. Fragments nudged outward may cross into zones where Earth's gravitational hold weakens relative to solar influence, making long-term retention uncertain. Those nudged inward encounter denser regions or stronger atmospheric drag, hastening descent. Solar radiation also contributes indirectly. Although far weaker than gravity in terms of force on larger bodies, sunlight exerts pressure on small grains, especially dust. Photons carry momentum. When absorbed or reflected, they impart subtle pushes. For fine particles within a ring, this effect can alter semi-major axes gradually, causing them to spiral inward through a mechanism known as Poynting-Robertson drag. The interplay between radiation and gravity ensures that no particle remains perfectly fixed. Earth, traveling along its orbit, carries its immediate environment through varying orientations relative to the Sun. This continuous change prevents solar tides from establishing stable equilibrium in the ring's structure. Instead, they perpetuate adjustment. The stress is gentle but unceasing, like a breath that never pauses. On human timescales, the alterations would be imperceptible. On geological timescales, they accumulate, guiding the system toward thinning and eventual dispersal. In this broader context, a ring cannot be understood as an isolated band confined to Earth's authority alone. It exists within the Sun's vast gravitational architecture, subject to forces that extend across astronomical units. Persistence requires resisting not only planetary pull and lunar disturbance, but also the constant solar tide that stretches and refines orbital space itself. Over long intervals, such refinement matters, shaping destiny through the quiet arithmetic of distance and force. Disappearance in orbit is rarely sudden. It unfolds as subtraction rather than collapse, a gradual thinning that escapes notice in any single moment. A ring does not shatter as a whole. It diminishes piece by piece, its edges softening first, its density lowering until structure becomes suggestion. The sky changes so slowly that only the arithmetic of time records the difference. Within the band, motion continues as it always has. Particles circle, collide, exchange energy. Yet with each collision, microscopic fragments are created, and with each exchange of momentum, subtle imbalances grow. Some pieces surrender altitude. As their orbital energy declines, their paths contract imperceptibly. They spiral inward, tracing tightening arcs that bring them closer to the planet's upper atmosphere. There, friction begins its quiet work. Air molecules, sparse but persistent, extract the last of their motion. Light flares briefly as material burns, and what remains descends to join the crust or ocean. Not all loss moves inward. Interactions among fragments occasionally lend energy to certain pieces at the expense of others. A particle can be nudged into a slightly higher orbit than another, crossing thresholds where planetary grip weakens relative to external forces. Solar tides and lunar perturbations amplify these outward journeys. Eventually, some fragments drift far enough to slip into independent paths around the Sun, or scatter into regions where their identities, as part of a ring, dissolve. Between inward fall and outward escape lies another, more complex fate. In zones where density remains high, particles may accumulate temporarily. Collisions cause them to stick, forming clumps that rotate as imperfect aggregates. For a time, these clusters resist dispersal, growing modestly as additional fragments adhere. Yet the same environment that allows brief assembly also seeds instability. Differential orbital speeds stretch the cluster. Tidal forces tug unevenly across its breadth. A stronger collision can fracture the whole back into constituent pieces. Assembly and disassembly alternate in quiet cycles, never fully resolving into permanence. As material is steadily removed through these channels, the ring becomes more transparent. Gaps widen where fragments once circulated densely. Lanes that were once distinct begin to blur as collision frequency decreases. Without continual replenishment, there is no mechanism to replace what is lost. The structure thins from within, density dropping below the threshold, where its presence meaningfully alters light or shadow. The timescale of this decay depends on composition and environment, yet the character of the process remains consistent. It is incremental. No final signal marks the moment when a ring ceases to qualify as a ring. Instead, there is a long interval during which it exists, ambiguously, present yet faint, influential yet diminishing. Only much later does absence feel complete. From the surface of the planet below, the change would have been almost imperceptible across individual lifetimes. Generations might see the same pale band overhead, unaware that its mass was slowly declining. Over thousands and millions of years, however, orbital statistics would tell a different story. The total material in circulation decreases, collisions become rarer, perturbations more decisive. In the end, what vanishes leaves little trace. Debris has returned to ground or dispersed into larger space. The forces responsible never cease. They simply complete their work gradually. A ring dies not through catastrophe, but through accumulation of small losses, its structure dissolving into the background of orbital motion until memory must rely on physics rather than sight. Nothing that circles a planet simply fades into abstraction. Matter follows trajectories until those paths intersect with gravity's deeper pull. When fragments lose enough energy to abandon stable orbit, they begin a descent that is as inevitable as their earlier ascent. The journey is not a straight fall, but a tightening spiral, each revolution carrying the particle lower than the last, its speed shifting in response to thickening layers of atmosphere. For the smallest grains, this return is almost luminous. As they encounter molecules high above the surface, friction converts motion into heat. The particles glow briefly, streaking across the sky in arcs so quick they leave only a memory of light. Most never reach the ground. They disintegrate into ionized trails that disperse and cool, contributing trace elements to upper air currents. Over extended intervals, this steady rain of dust alters atmospheric chemistry by imperceptible degrees, folding extraterrestrial material into terrestrial cycles. Larger fragments follow a different course. Their mass allows them to withstand the first phases of heating. As they plunge through denser air, compression ahead of the fragment raises temperatures dramatically. Outer layers melt and ablate, peeling away in incandescent sheets. Some bodies fracture mid-descent, scattering smaller pieces that spread the energy of impact across wider regions. Others endure intact, long enough to strike the surface, transferring kinetic energy to rock and water with sudden intensity. In the earliest ages of Earth, when surfaces were still reshaping and crust remained comparatively thin, such impacts would have left marks that later tectonics erased. Craters formed and were buried beneath new flows of magma, or altered by uplift and erosion. Debris that originated in orbit returned as molten droplets, glassy spherules, or solid stones embedded within evolving geology. The planet did not treat this material as foreign. It absorbed it, melting, mixing, and reincorporating it into mantle and crust. The scale of falling material would have diminished as the ring thinned. During periods when density remained high, re-entry events might have been frequent, producing continuous showers of small particles and occasional larger impacts. As mass declined, intervals between substantial returns lengthened, yet even sparse distributions guarantee eventual descent. Gravitational fields do not discriminate by size. They act persistently on every fragment that slows below sustaining velocity. Oceans, once stabilized, would have received some of this returning matter, integrating it into sedimentary layers. Fine particles settled through water columns, becoming part of chemical exchanges that shaped early marine environments. On land, fallen fragments contributed trace minerals to emerging crustal systems. Over geological timescales, the distinction between ring material and native rock blurred completely. The orbit that once encircled Earth became ground beneath evolving landscapes. This recycling underscores a simple continuity. The boundary between sky and surface is permeable over long periods. Material launched upward through violence does not remain suspended indefinitely. It revisits the world that expelled it. Each re-entry closes a loop in the broader circulation of matter, drawing orbit back into geology. In this way, disappearance does not imply annihilation. A fading ring leaves residues not as visible arcs above, but as integrated components below. Dust becomes air, stone becomes crust, energy becomes heat within the ground and ocean. The planet reclaims what once circled it, not through drama, but through the steady mechanics of descent, weaving former orbit into the fabric of Earth itself. Stone remembers, but it does not remember everything. The surface of Earth appears solid and enduring, yet it is in motion at scales too slow for daily perception. Continents drift upon convecting mantle. Ocean basins open and close. Crust forms, fractures, and descends back into the planet's interior. Within this restless system, traces of ancient events are rarely preserved intact. What once lay exposed becomes buried, altered, or consumed. Plate tectonics is the architect of this continual renewal. At mid-ocean ridges, new crust rises from molten sources, cooling and spreading outward in measured increments. Far from these ridges, plates converge and one descends beneath another, carrying surface material into depths where pressure and heat erase former identities. Rock that once bore witness to the sky can be melted, recrystallized, and reincorporated into mantle convection. Over hundreds of millions of years, the cycle repeats, thinning the archive of early history. Any debris that fell from a fading ring during Earth's youth would have landed upon a surface already in flux. Impact scars carved into thin crust could be obscured by volcanic resurfacing. Subsequent deformation might shear craters into elongated shapes or bury them beneath sediment. Even large basins, if formed during the earliest epochs, would have been subject to relentless modification as tectonic boundaries shifted and continents assembled. Erosion adds another layer of silence. Wind, water, and ice wear away elevated features, transporting particles from high ground to low. Mountains crumble into rivers. Rivers feed oceans. Oceanic sediments are eventually subducted and transformed. Fine material delivered from orbit would mingle with terrestrial sediments, indistinguishable from fragments produced by weathering. Over time, distinctive signatures disperse into broader geochemical backgrounds. Chemical alteration compounds the effect. Exposure to the atmosphere and hydrosphere changes mineral composition. Isotopic ratios can be reset through metamorphic processes. Even if ring-derived fragments possessed subtle chemical differences from underlying crust, prolonged cycling through Earth's dynamic systems would blur distinctions. Identifying their origin would require extraordinary preservation and careful interpretation, conditions rarely granted by deep time. The oldest surviving minerals on Earth are zircons embedded within younger rocks, their resilience allowing them to endure processes that consumed surrounding material. They offer glimpses into conditions over 4 billion years ago, yet even they carry incomplete narratives. If ring debris contributed to early sediments, the odds of direct recognition after billions of years of tectonic turnover are slim. The crust is not a static archive, it is an evolving manuscript, rewritten repeatedly. Ocean floors present even less opportunity for preservation. The majority of oceanic crust is relatively young in geological terms, rarely exceeding 200 million years before being recycled. Any early record stored there would have long since descended into the mantle. Continental cratons, more stable and ancient, retain deeper histories, but even they have been reshaped by orogenies, erosion, and metamorphism. Time exerts its own pressure, independent of tectonics and climate. The longer an event lies in the past, the more intervening processes obscure its outline. Layer upon layer of sediment accumulates. Subsequent deformation folds and faults those layers. Later uplift, exposes, and erodes them again. Each cycle redistributes material and alters context. In this landscape of continual transformation, orbital history leaves faint footprints at best. A vanished ring would not announce itself clearly within rock strata. Its material would be scattered, recycled, and transformed beyond simple recognition. Geological silence does not imply absence of past structure. It reflects the efficiency with which Earth reshapes itself, ensuring that even events written briefly across the sky can be absorbed into stone without preserving a clear trace. When direct evidence dissolves into deep time, inquiry turns toward patterns rather than objects. Scientists rarely expect to find a preserved fragment labeled by its origin. Instead, they examine distributions, alignments, and anomalies that hint at processes once active above a changing surface. In the absence of visible arcs in the sky, the search moves to textures within stone and statistics within crater fields. Impact patterns offer one avenue of approach. If a substantial band of debris once circled Earth, its gradual descent would not have struck randomly across all latitudes. Orbital geometry constraints, where falling fragments are most likely to re-enter. A ring aligned near the equatorial plane would preferentially deliver material within certain latitudinal bands. Over long intervals, this could create subtle clustering in impact structures or spheral deposits, patterns discernible only through comprehensive mapping and precise dating. No single crater would testify clearly, yet aggregated data might suggest directional bias. Ancient sediment layers provide another, more delicate archive. Microscopic spheres of once molten rock, known as spherules, have been discovered in Archean strata, preserved within sedimentary sequences that date back billions of years. Some originate from known large impacts, their chemical signatures tracing back to specific events. Others remain less easily classified. By examining isotopic compositions, mineral phases, and trace element ratios, researchers attempt to distinguish between local ejecta and material that may have orbited briefly before returning. The difference can be slight, encoded in ratios of oxygen isotopes or in anomalies of siderophile elements. Timing coincidences also attract attention. The early Earth experienced multiple large collisions and episodes of heightened bombardment. If a ring existed for a measurable interval, its decay should have overlapped with known geological phases. Scientists compare radiometric dates of impact deposits, shifts in sedimentation rates, and variations in atmospheric proxies. If clusters of reentry markers align temporally with models predicting ring dispersal, the convergence strengthens plausibility. Correlation does not guarantee causation, yet consistent timing across independent records invites closer scrutiny. Beyond the surface and stratigraphy, orbital mechanics leaves its own traces. The current angular momentum of the Earth-Moon system reflects a complex evolutionary history. By modeling tidal interactions backward through time, researchers estimate how rapidly the Moon receded and how Earth's rotation slowed. These calculations impose constraints on how mass was distributed in orbit during earlier epochs. A transient ring would have altered the moment of inertia and tidal dissipation parameters slightly, effects that could, in principle, be detected within refined dynamical reconstructions. Geochemical reservoirs offer further hints. Certain isotopic systems act as long-lived clocks, preserving ratios influenced by early high-temperature processes. If ring material experienced fractionation distinct from Earth's mantle, subtle deviations might persist in ancient zircon crystals or in deep crustal samples. Detecting such signals requires extraordinary precision and careful elimination of alternative explanations. None of these approaches promise clear affirmation. Each depends on piecing together indirect indicators that, taken alone, might be dismissed. The strength of the method lies in convergence. When unusual impact distributions, chemical anomalies, and orbital models align, they form a web of inference. Within that web, the absence of a visible ring does not equate to absence of history. Instead, researchers assemble probability from fragments of pattern, allowing physics and geology to speak jointly where direct remnants have long since been absorbed into the restless earth. Life responds not to singular events alone, but to averages accumulated over vast intervals. Energy arriving from the sun sets the fundamental pace of climate, and climate, in turn, frames the conditions within which chemistry becomes biology. When illumination shifts even slightly, the balance between warming and cooling adjusts. Over seasons, this may appear subtle. Over millions of years, it becomes formative. A circumplanetary ring would have modified the distribution of sunlight without extinguishing it. The alteration need not have been dramatic to produce consequence. A modest reduction in insolation across equatorial regions could temper evaporation rates, adjust atmospheric circulation, and reshape the boundaries between arid and humid zones. Conversely, regions outside primary shadow bands might experience small increases in scattered light, altering thermal gradients that drive winds and ocean currents. Climate systems are interconnected networks. A change in temperature at one latitude influences pressure systems elsewhere. Shifting rainfall patterns affect erosion, sedimentation, and nutrient delivery to emerging seas. Early microbial ecosystems depended on available sunlight for photosynthesis, a process exquisitely sensitive to light intensity and duration. Even fractional differences sustained over geologic time can favor certain metabolic pathways over others, encouraging diversification in some niches while constraining it in others. Ocean temperatures regulate solubility of gases such as carbon dioxide and methane. If a ring reduced average surface heating by a narrow margin, ocean chemistry could have shifted accordingly. Variations in dissolved gases influence atmospheric composition, and atmospheric composition feeds back into climate through greenhouse effects. These feedback loops amplify or dampen initial perturbations. What begins as a faint dimming overhead can cascade into reorganized climatic states. The earliest life on Earth emerged during eras when conditions were already in flux. Volcanism, impact activity, and tectonic adjustments created dynamic environments. Within such a landscape, an additional modulation of solar input might subtly steer evolutionary pathways. Regions kept slightly cooler could delay certain chemical reactions while favoring others. Thermal gradients within shallow waters might expand or contract habitable zones for microbial mats. Seasonal patterns shaped by orbital geometry could shift reproductive cycles and ecological interactions once multicellular organisms appeared. Evolution operates through differential survival across countless generations. A trait advantageous under one climate regime may be neutral or disadvantageous under another. If a ring persisted long enough to influence average temperatures or regional light cycles, it would contribute to the selective landscape. The influence would not announce itself visibly within fossils as a signature reading ring induced adaptation. Instead, it would be woven into broader patterns of diversification and extinction. Importantly, magnitude does not equate to impact in biological systems. Minor but sustained shifts often carry greater evolutionary weight than brief extremes. A ring need not cloak the world in shadow to matter. Its presence could recalibrate the distribution of energy in ways that reshape ecological boundaries, gradually guiding the development of complex interactions. As the ring thinned and disappeared, climates would readjust again. Life would respond as it always has, adapting to the new equilibrium. In this interplay between orbit and organism, sky and cell, small astronomical variations become threads within the larger tapestry of Earth's living history, influencing outcomes through persistence rather than spectacle. Across the inner solar system, silence in the sky does not imply an unbroken past. Earth is not the only world that has endured collision, dispersal, and rearrangement. Planetary history unfolds through similar physical laws wherever mass and motion intersect, and the processes that create and dissolve rings operate far beyond a single orbit. Mars offers a quiet example. Today it carries two small moons, Phobos and Deimos, irregular and dark, tracing close paths above a rust-colored landscape. Phobos in particular circles so near that tidal forces are steadily drawing it inward. Models of its future predict fragmentation once it crosses a critical distance, its rubble torn apart into debris that will briefly form a ring before spiraling down toward the surface. In this projected outcome, Mars would wear a transient band of material, not as ornament, but as consequence. The physics mirrors processes already described around Earth, suggesting that ring phases may arise naturally during planetary evolution. Elsewhere, the gas giants display rings openly, yet even there, permanence is an illusion. Saturn's luminous system is constantly replenished by collisions among icy moons and ring particles, but measurements indicate gradual loss through inward drift and atmospheric absorption. Jupiter's faint rings are fed by micrometeoroid impacts that grind material from small inner satellites. These examples reveal not stability, but balance maintained through ongoing input. Without renewal, decay would proceed. Beyond our solar system, observations of young planetary systems show disks of dust and debris encircling newly formed worlds. Infrared signatures and direct imaging reveal structures that resemble scaled-down versions of stellar accretion disks, suggesting that ring-like configurations are common byproducts of formation and collision. In these distant systems, the distinction between disk and ring blurs. Yet the principle remains consistent. Material trapped in orbit under tidal constraints organizes into bands, then evolves as gravitational interactions reshape it. The common thread across these varied worlds is not possession of rings, but passage through them. Formation events, impacts, and tidal disruptions create circumstances in which debris must orbit. Whether that debris persists depends on mass distribution, external perturbations, and availability of replenishing sources. Larger planets with extensive satellite systems may sustain rings longer, especially if ongoing collisions among moons supply fresh material. Smaller terrestrial planets with limited reservoirs and efficient clearing mechanisms may pass through ring phases more swiftly. Comparative modeling strengthens this view. Simulations of planetary accretion frequently generate temporary circumplanetary disks following major impacts. Some disks consolidate into moons, others dissipate entirely. The transition from chaotic early conditions to settled orbital architectures appears to include ring-like intervals as common steps rather than rare anomalies. The rarity lies not in formation, but in endurance. Thus, Earth's present emptiness above does not isolate it from broader planetary narratives. It situates it among worlds that have likely hosted ephemeral structures now absent. Ring survival demands a precise alignment of replenishment and containment. In most systems, forces promoting decay eventually outweigh those maintaining density. The sky clears, not because rings never formed, but because the dynamics that created them also ensure their eventual thinning. In this wider context, a vanished terrestrial ring would represent not a singular curiosity, but a familiar stage in planetary development. The silence overhead becomes part of a shared pattern across worlds, where rings emerge naturally from collision and gravity, then fade as equilibrium settles, leaving only physics to testify to their passing. In the long arc of planetary evolution, few characteristics remain fixed from birth to maturity. Worlds assemble from debris, differentiate into layered interiors, and gradually settle into quieter orbits as the surrounding environment clears. Along this trajectory, structures may emerge that later disappear, not because they were improbable, but because they belonged to a different chapter of development. A ring can be understood within this context, less as an enduring trait and more as a temporary arrangement shaped by circumstance. Early stages of planet formation are marked by abundance of loose material. Collisions are frequent, velocities high, and gravitational interactions complex. Under such conditions, debris cannot avoid orbiting configurations. Fragments generated by impact or tidal disruption naturally organize into disks and bands while angular momentum is redistributed. A ring in this phase reflects ongoing assembly and adjustment. It signals that material remains unsettled, still negotiating its place within a gravitational hierarchy. As time advances, the environment simplifies. Major bodies either merge or are ejected from unstable paths. The remaining planet and its satellites occupy more stable orbits. Sources of fresh debris diminish, and the cumulative effects of drag, perturbation, and collision begin to outweigh processes of replenishment. In this calmer setting, a ring no longer thrives. Without sustained input, it thinks, its presence becomes increasingly difficult to maintain against forces that favor consolidation or dispersal. This progression suggests that rings are often transitional. They emerge during intervals when systems are reorganizing and decline once equilibrium strengthens. The distinction between a world with rings and one without may therefore reflect timing rather than fundamental difference. A planet observed during its formative turbulence might display a bright or muted band of orbiting material, while the same planet viewed hundreds of millions of years later would appear bare. Stability exerts a subtle discipline. When large-scale impacts grow rare and orbital resonances settle into predictable patterns, loose debris encounters fewer opportunities for renewal. Satellites that survived earlier chaos continue to shape the gravitational field, clearing remnant material through resonant interactions. Atmospheric drag removes low orbit fragments, and solar tides refine outer boundaries. Each process contributes to simplification. What remains is a configuration dominated by a planet and any consolidated moons, absent the diffuse bands that once bridged the gap between formation and settlement. Understanding rings as phases rather than permanent features reframes how planetary history is interpreted. The absence of a ring today does not negate the possibility of its earlier existence. Instead, it may signal that the planet has moved beyond the conditions that sustain such a structure. Conversely, the presence of a ring elsewhere might indicate an ongoing or recent episode of disruption rather than inherent uniqueness. Across cosmic timescales, transitions outnumber constants. A ring embodies a moment when matter lingers between dispersal and assembly, when energy redistribution has not yet resolved into enduring architecture. As gravitational systems evolve toward lower states of dynamic instability, temporary features yield to longer-lived arrangements. In this light, rings become chapters rather than identities, expressions of motion and adjustment that fade as planets advance from youth toward relative quiet. Silence above a planet often signals resolution rather than omission. The absence of a ring around Earth today reflects a system that has progressed beyond its most chaotic epochs. After the era of frequent collisions and orbiting debris, the inner solar system gradually thinned. Large wandering bodies were either incorporated into planets, expelled into distant trajectories, or shattered into smaller fragments that no longer posed global threats. With each passing million years, the rate of massive impacts declined, reducing the primary mechanism that once supplied fresh material to near-Earth space. As bombardment waned, the gravitational architecture of the Earth-Moon pair matured. The Moon continued its steady outward drift, a consequence of tidal interactions that exchange angular momentum between Earth's rotation and lunar orbit. While this migration altered certain dynamical relationships, it also carried the Moon into a configuration that promotes long-term stability. Orbital resonances that might have sustained chaotic redistribution of debris became less disruptive over time. The broad sweep of gravitational influences settled into predictable rhythms. Earth's own clearing processes compounded this shift. Without repeated injections of new fragments, the residual material in orbit faced ongoing decay through atmospheric drag, collision-driven energy loss, and solar and lunar perturbations. Gradual thinning reduced density below levels required to maintain a coherent band. Any remaining particles either descended to the surface or migrated outward until dispersed beyond significant influence. The balance tipped decisively toward simplification. Geological evolution mirrored these orbital changes. As the crust thickened and plate tectonics established steady patterns, surface conditions became less extreme. Oceans persisted and atmospheres evolved, moderating global temperatures. Stability at the surface did not directly eliminate a ring, yet it marked the broader transition from formative turbulence to comparative calm. A quieter planetary environment lacks the energetic events that might regenerate extensive debris structures. In addition, the gravitational interplay between Earth and Moon constrained the potential for future large-scale disruption close to the planet. The presence of a substantial satellite alters trajectories of incoming objects, capturing some and deflecting others. While not a shield in the literal sense, this arrangement modifies collision probabilities within specific orbital corridors. Over extended timescales, such influences contribute to reduced accumulation of near-Earth debris. The combined outcome of diminished bombardment, efficient gravitational clearing, and stabilized orbital relationships is the uncluttered sky observed today. Nothing persists indefinitely without renewal. A ring requires either continual fragmentation of nearby bodies or sustained capture of fresh material. Earth, having moved beyond its era of widespread collision and having consolidated most major orbiting mass into a single moon, no longer supplies or retains the debris necessary for such a structure. Calm does not imply inactivity. The planet continues to evolve, its rotation slowly lengthening days, its continents drifting at measured pace, its atmosphere exchanging gases through biological and chemical cycles. Yet in the realm of orbital architecture, the system exhibits a settled configuration. Energy flows remain, but large-scale rearrangements have become rare. Thus, the sky's emptiness is not an oversight of cosmic design. It is a record of processes completed. Earth progressed from a state where debris circled in abundance to one where gravitational forces had largely completed their sorting. In that progression, the conditions favoring a persistent ring diminished until they vanished, leaving a planet defined by a single enduring companion and a surrounding space shaped more by stability than by scatter. The conditions that define the present often feel timeless, yet they rest upon a narrow window within a far longer continuum. Earth today appears composed and predictable, its rhythms measured by seasons, tides, and the steady return of sunrise. Orbital paths have settled into durable patterns, catastrophic collisions are rare, the architecture of the Earth-Moon system unfolds with quiet regularity. In this calm, it is easy to mistake stability for permanence. Yet geological and astronomical records tell a different story. The early history of this planet was marked by upheaval, shifting configurations, and environments that bore little resemblance to what now feels familiar. Continents did not yet hold their modern outlines. Oceans condensed, evaporated, and condensed again. Impacts reshaped surfaces and altered rotation. The sky above participated in this transformation, reflecting arrangements of matter that no longer persist. A familiar horizon is therefore a recent achievement. Relative tranquility emerged gradually as the solar system matured and cleared itself of excess debris. The pathways once crowded with colliding bodies thinned. Massive rearrangements gave way to incremental adjustments. The moon, born of violence, became a stabilizing influence over axial tilt and rotational behavior. Atmospheric composition evolved through volcanic outgassing and biological feedback, moderating temperature extremes. Each development contributed to a cumulative shift from volatility toward balance. Even so, the equilibrium of the present remains contingent. Planetary systems are dynamic on scales beyond human memory. Orbital parameters evolve under gravitational influence. Ice ages advance and retreat in response to subtle variations in Earth's tilt and orbital eccentricity. Solar luminosity increases gradually over billions of years. What appears constant within a few generations is part of an ongoing negotiation between internal processes and external forces. The absence of dramatic structures in the sky reinforces the impression of completion. A single moon traces its arc, planets wander predictably against the stars. Yet the earlier chapters of Earth's history, suggests that such clarity was not always the rule. Periods of debris encircling the planet, heightened bombardment, and unsettled atmospheric conditions formed part of the journey toward present calm. The sky itself has changed character over time, shaped by shifting distributions of matter. To recognize stability as earned is to acknowledge the accumulated work of gravitational sorting, tectonic recycling, and atmospheric evolution. The system did not begin in equilibrium. It progressed toward it through repeated adjustment. Temporary features faded, enduring arrangements strengthened. This progression does not eliminate the possibility of future change. It merely situates the present within a broader arc. The perspective gained from deep time reframes normality. What feels foundational may be transient when measured against planetary history. Long intervals of relative quiet can follow intense upheaval, yet they remain embedded within ongoing dynamism. Earth's current serenity is the outcome of processes that consumed earlier instabilities and organized them into sustainable patterns. In this light, the world we inhabit represents a refined phase rather than an original state. Its balanced climate, settled orbits, and unobstructed sky reflect a stage reached after epochs of transformation. Stability stands not as a guaranteed backdrop, but as a condition achieved through the gradual reduction of chaos, preserved for now within the evolving architecture of a maturing planetary system. A planet is often imagined as a finished object, a sphere set in motion and left to persist unchanged across the ages. Yet every world carries within it the memory of transition. Composition shifts, internal layers reorganize, and surfaces transform beneath the combined pressure of gravity, heat, and time. What appears solid and stable is, in fact, the current expression of an ongoing process. During formation, planets accumulate mass through collision and accretion. Their interiors differentiate as heavier elements sink and lighter materials rise. Atmospheres emerge, sometimes only to be stripped away and replaced. Early conditions are rarely representative of the mature state that follows. Instead, infancy is marked by volatility, by rearrangement of orbiting bodies, and by exchanges of energy that reshape entire systems. Within this turbulence, transient features naturally arise. As energy dissipates and debris clears, a planet enters a different phase. Impacts become less frequent, orbital resonances settle, and heat escapes gradually into surrounding space. The internal engine slows. Tectonic cycles establish rhythms. Climates stabilize within narrower bounds. Structures born of chaos, such as extended disks of debris or dense swarms of fragments, thin and disappear when no longer replenished. The shift is not from complexity to emptiness, but from multiplicity to coherence. Loss, in this context, is not a defect. It is a form of refinement. A ring may represent a moment when mass is distributed widely across near space, tracing arcs that signal ongoing rearrangement. When that ring fades, it reflects the consolidation of material into more stable arrangements or its removal entirely from the immediate system. The architecture simplifies not because the system diminishes, but because dynamic excess has been resolved. Other planetary features follow similar arcs. Thick primordial atmospheres can be eroded by solar wind or transformed by chemical processes. Magnetic fields may strengthen and weaken as internal convection evolves. Surface oceans can form, evaporate, freeze, and reform depending on stellar luminosity and atmospheric composition. Each state represents a phase within a longer narrative rather than a permanent identity. Time acts as a filter. Over billions of years, unstable configurations are less likely to endure. What remains visible in the present is often the subset of structures capable of persisting under prevailing conditions. This selective endurance creates an impression of constancy, yet it masks the succession of prior arrangements that preceded it. Planets are shaped as much by what they have shed as by what they retain. Understanding worlds as dynamic systems alters the lens through which absence is interpreted. A missing feature need not imply impossibility. It may instead indicate that the window during which it existed has closed. The trajectory from formation to maturity includes episodes of dispersal and consolidation, of addition and subtraction. Rings, atmospheres, and even surface oceans can occupy temporary chapters within that progression. Across the cosmos, countless planets are likely moving through different stages of similar cycles. Some may presently host bright, dense rings formed by recent disruption. Others may display no trace of earlier debris that once encircled them. Variation in observed features reflects diversity of timing rather than fundamental divergence in physical law. In this way, the study of planetary evolution becomes a meditation on change. States shift, configurations resolve, structures simplify. What endures does so because it aligns with the long-term equilibrium of the system. Planets are not static monuments in space. They are evolving bodies, continuously shaped by the interplay of gravity, energy, and time, revealing their histories through both presence and absence. Some histories leave monuments. Mountain ranges announce past collisions of continents. Fossil beds preserve the silhouettes of vanished creatures, and craters trace the memory of sudden descent. Other histories pass without such markers. They unfold above the surface in regions that do not fossilize and cannot be quarried for evidence. When they fade, they leave little more than altered probabilities and rearranged motion. An orbital structure that once encircled a young planet would belong to this quieter category. It would not carve valleys or deposit bones. It would not stand as a ruin awaiting excavation. Its material, if it descended, would blend seamlessly with crust and ocean, indistinguishable from rock born directly of volcanic fire. The sky, having cleared, would offer no visible relic to hint at what once traced its horizon. Photographs exist only for moments captured within the last century and a half of human inquiry. Deep time has no archive of images. A vanished ring, if present billions of years ago, lies beyond any camera's reach. Telescopes can reveal rings around distant worlds today, yet those images do not extend backward through Earth's own history. The absence of visual record does not negate possibility. It merely reflects the limits of observation. Fossils preserve life that interacts with sediment and water. An orbital band interacts primarily with gravity and light. Its signature, if any, must be detected in subtle deviations, in the distribution of impact spherules, in isotopic ratios that whisper of high-temperature origin. Such traces require interpretation rather than direct sight. They demand comparison between model and measurement, between predicted pattern and observed anomaly. Monuments of stone endure because they are embedded within geology. A ring exists in motion, sustained by balance rather than solidity. When that balance tips, the structure disperses without leaving a single enduring fragment that proclaims its former unity. The fragments become ordinary rock. The unity dissolves into statistics. Time then folds these statistics into broader patterns until only careful analysis can disentangle them. This story is therefore easy to overlook. It lacks spectacle preserved in strata, It does not align with dramatic extinction boundaries or conspicuous mineral layers easily traced across continents. Instead, it resides within equations describing orbital decay, within simulations of early impacts, within delicate measurements of ancient isotopes. Its evidence is cumulative rather than singular, emerging from the convergence of mechanics and geology rather than from a single decisive discovery. Physics, however, retains memory in its own way. The conservation of angular momentum, the dynamics of tidal forces, and the modeled evolution of planetary systems all constrain what could have occurred. Inference built upon these principles forms a lattice of plausibility. While rocks may not shout of a former ring, gravitational equations do not forget the pathways through which such a structure would evolve and dissolve. Understanding such a narrative requires patience with abstraction. It asks that absence be considered alongside presence, that silence be weighed as carefully as proclamation. In a universe governed by consistent laws, some chapters are recorded in stone, others in motion. When motion ceases to trace visible arcs, only the quiet language of physics remains to suggest what once circled above. There is a quiet illusion woven into everyday experience, the sense that the world, as it appears now, represents a settled final draft. The continents seem anchored, the oceans contained within familiar shorelines, the sky composed of repeating patterns that feel dependable. These impressions cultivate a subtle belief in permanence, as though the present configuration were the intended design rather than a fleeting arrangement within a longer unfolding. Yet permanence is not a property planets possess. It is a perception shaped by the brevity of human timescales. Geological records reveal coastlines that once lay far inland, mountain ranges worn down to plains, and climates that oscillated between extremes. Atmospheric compositions have shifted dramatically, transforming the chemistry of oceans and the structure of ecosystems. Even the length of a day has gradually increased as rotational energy transfers outward. Each alteration unfolded slowly enough to evade immediate notice, yet collectively they testify to continual change. Orbital structures follow the same principle. Features that seem stable within an epoch may be temporary when measured against billions of years. Debris that once circled can thin and descend. Magnetic fields that shield atmospheres can weaken. Moons can migrate, approaching or receding depending on tidal exchanges. What endures does so only while forces remain in balance. Once equilibrium shifts, transformation proceeds. Earth has already surrendered elements that defined earlier stages of its existence. A primordial atmosphere rich in hydrogen and helium was lost to space. Vast quantities of internal heat have dissipated since formation, altering convection patterns within the mantle and core. If a circumplanetary ring ever traced the sky, it too would have yielded to gravitational clearing and decay. Loss in planetary evolution is neither rare nor exceptional. It is integral to development. The present calm does not exempt the future from similar transitions. Solar luminosity will continue its gradual rise, influencing climate over extended intervals. Tidal interactions will keep adjusting the Earth-Moon relationship, lengthening days incrementally. Plate motions will reorganize continents into new assemblies. None of these processes imply imminent catastrophe. They simply reflect continuity of change. Assuming permanence can obscure appreciation for this dynamism. When the world appears fixed, it becomes easy to overlook the slow accumulation of subtle shifts. Stability may persist for millions of years, yet it remains contingent on underlying mechanisms that themselves evolve. Planets simplify as they age. shedding unstable configurations. But simplification does not equate to finality. It represents a stage achieved under current conditions. Recognizing temporality does not diminish the significance of the present. Instead, it situates it within a broader narrative. The features that define Earth now emerged from earlier volatility, and they will eventually yield to new arrangements shaped by gravity, radiation, and internal processes. The sky's clarity, the orbit's predictability, the balance between land and sea all exist within parameters that can and will adjust over deep time. In viewing Earth as an evolving system rather than a finished artifact, the illusion of eternity softens. What is visible today becomes part of an ongoing cycle of acquisition and release. The planet has already relinquished much that once characterized it, and further relinquishments lie embedded within physical law. Continuity resides not in any single feature, but in the persistent movement through states that define planetary life across cosmic spans. Endurance, at planetary scale, is measured not in moments, but in epochs. To survive is not merely to persist unchanged, but to pass through upheaval and emerge reorganized. Earth's history is layered with episodes of collision, melting, atmospheric loss, and orbital rearrangement. None of these phases were gentle. Each imposed stresses that could have prevented long-term continuity, yet the planet did not remain locked in those extremes. The earliest chapters were defined by impact and heat. Massive bodies collided, releasing energy that liquefied rock and reshaped rotation. Material was stripped away, redistributed, or forced into new configurations. In such conditions, survival meant retaining sufficient mass and angular momentum to remain gravitationally coherent. Earth did so. Its core settled, its mantle differentiated, and its surface eventually cooled enough to sustain crust. Adaptation at a planetary level differs from biological adaptation, yet the analogy holds in a broader sense. Systems respond to perturbation by reorganizing. When bombardment lessened, internal processes assumed greater prominence. Volcanic outgassing contributed to atmosphere formation. Water condensed, accumulating in basins shaped by tectonic motion. Chemical cycles established feedback loops that regulated temperature within bounds compatible with liquid oceans. None of these outcomes were guaranteed. They represent pathways taken under specific physical constraints. Instability gradually diminished as energy was redistributed and excess debris cleared. What began as a crowded environment of intersecting trajectories simplified into more ordered motion. Resonances stabilized, catastrophic rearrangements became rarer, and orbital relationships matured. The transition from turbulence to balance was not instantaneous. It unfolded across vast intervals, with each adjustment building upon prior structure. In shedding instability, Earth did not lose identity. It refined it. Features that could not be maintained under prevailing conditions faded. Others consolidated into enduring forms. A thick, reducing atmosphere gave way to one transformed by biological activity. Repeated resurfacing by impacts was replaced by slower tectonic recycling. If circumplanetary debris once lingered, it eventually resolved into more stable configurations, or returned to the planet below. The persistence of liquid water across billions of years stands as a marker of this successful navigation through change. Maintaining oceans required a delicate balance between solar input, greenhouse gases, and internal heat flow. Deviations occurred, including global glaciations and warmer greenhouse intervals, yet the system avoided irreversible extremes. Feedback mechanisms acted as stabilizers, damping fluctuations that might otherwise have driven runaway conditions. Survival also reflects context. The sun's relatively stable luminosity and the gravitational architecture of the solar system contributed to sustained habitability. Earth's distance from the sun positioned it within a range where water could persist in liquid form. The presence of a large moon influenced rotational stability, moderating axial tilt over time. These factors did not eliminate volatility, but they provided parameters within which adaptation could unfold. What remains today is the cumulative product of these responses. The planet's current state embodies outcomes of prior challenges absorbed and reconfigured. Continents drift but do not disintegrate. The atmosphere circulates but does not escape wholesale. Orbit persists within predictable bounds. Such characteristics represent the residue of countless adjustments. To view Earth as a survivor is to recognize that its present calm was not inherited intact. It was achieved through repeated accommodation to forces capable of erasure. Violence did not define the final state. It shaped the path toward it. Adaptation did not signify weakness. It enabled continuity. The world we inhabit reflects a sequence of thresholds crossed and instabilities resolved, a testament to persistence expressed through change rather than stasis. Not every ending is marked by spectacle. Some dissolve without a sound, their presence thinning so gradually that there is no instant one can point to and call the last. A planetary ring, if it ever encircled Earth, would not have ended in fire or fracture. It would have surrendered itself in increments, its boundaries softening until they were indistinguishable from emptiness. Rings persist only through motion and balance. Countless fragments trace paths defined by gravity, each orbit a negotiation between forward velocity and inward pull. As time advances, collisions among those fragments redistribute energy. Tiny adjustments accumulate. A particle slowed by impact drops slightly lower, encountering denser regions where further interactions hasten its descent. Another fragment may gain energy and drift outward, crossing thresholds that carry it away from the coherent band. No single alteration matters alone, yet together they reshape the structure. Gradual absence begins as thinning. Gaps widen between particles. Once continuous arcs become porous. From a distance, the ring might still appear intact, but its density declines beyond what can sustain unity. Without replenishment from new debris, loss proceeds unopposed. Material spirals inward through atmospheric drag or gravitational perturbation. Some fragments evaporate as they meet the upper atmosphere, their substance folded quietly back into Earth's surface. Others disperse outward, absorbed into broader orbital pathways until their shared geometry dissolves. There is no final revolution that signals completion. Instead, the number of fragments tracing similar paths simply diminishes. What once required millions of particles to define a band becomes thousands, then hundreds, then too few to register as a structure. One orbit less, then another, until the collective pattern no longer manifests. Motion continues, but organization has faded. The dynamics that govern this process are patient. Tidal interactions, resonance effects, and minute variations in gravitational field operate continuously. Over thousands or millions of years, their cumulative influence becomes decisive. A ring's coherence depends on the interplay of these forces. When that interplay favors dispersion, the result unfolds slowly and without ceremony. Stability for the planet emerges as instability for the ring. From the surface below, the change would not arrive as a sudden clearing. Generations might pass without perceiving any difference. If early observers existed, They would witness a sky subtly altered over intervals too long for memory to retain comparison. Eventually, the band would no longer arc overhead. The heavens would appear open, and the absence would feel ordinary. What remains after such an ending is not debris arranged in symmetry, but a system simplified. The energy once distributed across countless fragments has been transferred, dissipated, or reabsorbed. The planet continues its orbit around the sun. The moon follows its own path, and space between them lies comparatively uncluttered. Nothing announces that a structure once bridged that space. In this way, the conclusion of a ring exemplifies a broader principle of planetary evolution. Change often arrives as gradual subtraction rather than abrupt collapse. Structures formed through chaos dissolve through calm. The final state appears serene, though it carries within it the history of what has been relinquished. The end comes not as an event, but as quiet completion. Silence can carry as much meaning as sound. In planetary science, what is missing often reveals as much as what remains. An uncluttered sky, a simplified orbit, a system reduced to a few dominant bodies, each speaks of prior sorting, of forces that have already done their work. Absence is not emptiness, it is the imprint of processes completed. When debris no longer encircles a planet, that absence reflects a history of interaction. Gravitational clearing, collision-driven decay, atmospheric drag, and tidal redistribution do not act invisibly in principle, even if their results leave no visible monument. The current configuration of Earth and Moon embodies outcomes of these mechanisms. The spacing between bodies, the stability of their orbits, and the scarcity of lingering fragments all encode previous states within their geometry. Loss leaves structure behind in subtler forms. Angular momentum transferred outward lengthens days and widens lunar distance. Impact-generated materials alter isotopic ratios within rocks. Thermal histories, preserved in mineral crystals, record episodes of melting and cooling that align with massive collisions. These traces do not announce a ring explicitly, yet they constrain what must have occurred in early epochs. Patterns of motion and composition serve as residues of rearrangement. Even the regularity of present tides contains embedded narrative. The gravitational partnership between Earth and Moon evolved through exchanges that dissipated energy and reshaped rotation. If large quantities of orbiting material once existed, their interactions would have influenced this evolution. The current state reflects a trajectory shaped by earlier mass distribution, whether consolidated into a moon or dispersed and reabsorbed. Comparative planetary science strengthens interpretation. By studying rings around other worlds and modeling their formation and decay, researchers establish templates for how such systems behave. These templates allow reconstruction of plausible histories even in the absence of direct observation. The logic resembles that of archaeology, conducted through dynamics rather than artifacts. Structures of motion replace broken pottery. Conservation laws substitute for inscriptions. The present thus holds layered clues. A planet's simplified architecture can imply that unstable configurations have already been resolved. The rarity of near-orbit debris, the dominance of a single large satellite, and the long-term coherence of orbital parameters collectively suggest that earlier excess has been shed. Each element contributes to a portrait of maturation. Absence also sharpens awareness of contingency. Features that are no longer visible remind us that planetary systems evolve through gain and relinquishment. What remains is shaped not only by what formed successfully, but by what failed to persist. In this way, Loss sculpts identity as much as accumulation does. To read these signals requires attention to subtlety. The clues are distributed across measurements of rotation rates, orbital distances, mineral compositions, and impact frequencies. None alone confirms a vanished structure. Together, they outline boundaries of possibility. Within those boundaries, a narrative can be inferred that aligns with known physical laws. What we learn from what is missing is an appreciation for process over snapshot. The current Earth-Moon system stands as a product of earlier configurations now erased from direct sight. Its calm symmetry, its clear orbital space, and its enduring stability point backward to transitions already navigated. In planetary history, absence is not silence. It is testimony expressed through the ordered simplicity that follows change. It is possible to look upward and mistake simplicity for origin. A dark expanse punctuated by a single moon can feel foundational, as though this arrangement were written into the architecture of the universe from the beginning. The emptiness between Earth and its satellite seems complete, uncluttered, resolved. Yet context alters perception. When orbital history is layered into that view, the apparent simplicity becomes a later chapter rather than a starting point. The present sky reflects a matured system. Gravitational interactions have sorted what once may have been distributed more widely. Material either coalesced into enduring bodies or drifted away through processes that favor consolidation and clearance. Recognizing this progression transforms absence into evidence. What is not there becomes part of the narrative rather than a void outside it. A viewer aware of planetary evolution does not see only darkness between Earth and Moon. Instead, they perceive the dynamic interplay that once shaped that space. Tidal forces, collision fragments, angular momentum exchange, and gradual decay each contributed to the current configuration. The calm interval overhead is a consequence of those prior adjustments. The emptiness is structured by laws that ensured transient arrangements would not persist indefinitely. This broader frame does not require direct visual trace. It rests on understanding that systems evolve through states of higher and lower dispersion. Early phases often involve surplus material circulating in unstable paths. Later phases display reduced complexity as unstable trajectories are eliminated. Seen from this vantage, a clear sky becomes a marker of age and resolution. Such awareness also extends outward to other worlds. Observing rings around distant planets reveals stages that Earth may have once shared. The contrast between their visible bands and our uncluttered horizon underscores the diversity of timing rather than of possibility. Different worlds occupy different points along similar physical pathways. Context allows these comparisons to illuminate rather than confuse. What we do not see matters because absence shapes equilibrium. A ring would alter light distribution, gravitational interactions, and debris dynamics. Its disappearance implies adjustments already absorbed. The current balance between Earth and Moon, the stability of rotational cycles, and the rarity of substantial near-orbit debris all speak to a system that has transitioned beyond an earlier configuration. Looking upward with this perspective encourages patience with subtlety. The sky becomes less a static backdrop and more a record of prior motion distilled into simplicity. Every clear interval between objects has been carved by processes that removed what could not endure. The present arrangement carries within it the memory of those removals, encoded not in bright arcs, but in measured distances and regular tides. In this sense, context deepens rather than complicates appreciation. The unadorned sky is no longer merely familiar. It is the outcome of gravitational refinement. The absence overhead becomes part of a coherent story of formation, excess, and resolution. What is unseen gains significance through the understanding that it once may have been otherwise, and that the path to this quiet clarity was neither immediate nor inevitable, but achieved through persistent, law governed change. Every landscape carries invisible layers of memory. Beneath forests and oceans lie traces of older worlds, configurations that shaped what followed and then yielded to new arrangements. Earth today presents itself as balanced and composed, defined by continents, seas, and a single faithful moon. Yet this image represents only one frame within a far longer sequence. There was a time when land had not yet hardened into recognizable continents, when oceans were vapor or rain suspended in a volatile sky. There may have been epochs when fragments circled overhead, temporary halos born of impact and gravitational negotiation. Such features, if they existed, belonged to moments of transition. They reflected a planet still deciding its architecture, still distributing mass and energy into forms that could endure. Temporary does not mean trivial. A feature can shape climate, influence motion, and redirect the course of development, even if it does not last. Debris encircling a young world would have participated in tidal exchanges, altered light distribution, and contributed material back to the surface. Its presence would have been one thread among many, woven into the tapestry of Earth's evolution. When that thread dissolved, it left the larger pattern subtly changed. Other elements proved more persistent. The consolidation of a large moon established a long-term gravitational partnership. Plate tectonics sustained cycles of renewal across the crust. The hydrological system balanced evaporation and rainfall in a steady rhythm. These enduring processes now define what feels ordinary. Their survival does not reflect inevitability, but compatibility with the evolving equilibrium of the system. What we call normal is simply what remained after instability resolved. The absence of certain features, the endurance of others, and the steady narrowing of chaotic possibilities produced a configuration that appears settled, yet it is settled only relative to earlier turbulence. Deep time reminds us that the present condition arose from selection through physical law. Unstable arrangements faded, sustainable ones persisted. This perspective softens the boundary between imagination and inference. Considering that Earth might once have worn a ring does not require dramatic imagery or speculative excess. It follows from acknowledging that planets form through collision, that debris must orbit, and that orbiting debris decays. Whether such a structure endured long or briefly, its possibility aligns with the processes already known to shape worlds. The sky above now feels spare and complete. Its clarity invites the assumption that it has always been so. Yet the path to this clarity likely included excess, dispersion, and gradual refinement. Recognizing that journey does not diminish the beauty of the present arrangement. It enhances it, grounding simplicity in history rather than in assumption. Earth once carried more than land and sea, more than the patterns we memorize in textbooks and calendars. Some features were fleeting, marking phases of adjustment. Others proved resilient, anchoring the planet through changing eras. The world we inhabit is the outcome of those negotiations, the visible result of countless transitions, now folded into quiet stability. In the end, normal is not a starting point, it is a survivor.